Hello, everybody. Thank you for coming to our talk on simplifying the adoption of generative AI for enterprises. Just a little introduction to ourselves. My name is Peter Dykes. I'm a solutions architect at NVIDIA. I focus mostly on multimodal learning and large-scale training. And this is my co-presenter, Jahang, who is our expert in inference. He'll be going over that in the second half of the talk. Just wanted to start with a little agenda for today. So we're going to be starting out with kind of some of the work that our team does with AWS and some of the collaborations we've done with generative AI. Then some of the NVIDIA AI on AWS, some of the software we have, some of the hardware we have. And then we'll go into some of the frameworks we have. So we'll all start out with some at-scale training on AWS. How do we scale out? How do we make everything efficient? And then Jahang will take it from there with our deployment with Triton and some of our acceleration with TensorRT. And then at the end, we'll have some call to action and other conclusions to take from the talk. So the first thing I want to start with is that NVIDIA isn't just a hardware company. We're a full stack AI company as well. So we have optimized containers. We have optimized software for all different types of use cases across the board. And it all stacks up. So you can think of your frameworks at a low level where we've optimized for PyTorch, for TensorFlow, for JAX. And then we also have frameworks on top of this. So one that we'll be going into today would be the NeMo framework for generative AI, but we also have other ones like Merlin for recommender systems. We have BioNeMo for bio use cases, and across the board, we have tons of different frameworks that we can use at higher levels for some of these different use cases in industries as well. So it's not just a hardware company. We also are kind of trying to optimize across the board from our software as well. So just to start with our collaboration from NVIDIA and AWS. And so we have a bunch of different GPUs all the way from the cloud to the edge that we offer. So at a higher level, the most performance you have is the P5 instance, which is the H100 instance that's offered right now. So this is where you can do all of your large-scale training and HPC works that you need the highest end GPUs with the most performance and the most memory. And then we also have other instances, such as the G5 instance, which is the A10G GPU from NVIDIA that's used a lot for ML inference. It's a little smaller, but it's great for inference and for cost performance benefit. And then again, we also have for the graphics workloads, we have the T4G, which is also T4 GPU by NVIDIA as well. And then you can also use the Triton inference server that we're going to go over later for deploying your models, for managing all your requests and batching all of that. And that also integrates with SageMaker, is something that our team and Jahang has worked on as well to make it as seamless to be able to deploy models on SageMaker as well. And then you can also go all the way to the edge with our Jetson platform. So these are embedded devices. So you can train on one of these higher-end GPUs for training, and then you can deploy it at the edge for GPUs with Jetson as well. And all of this optimized software is offered on the AWS marketplace as well. So one of the use cases that we've actually worked on is the Amazon catalog team. And so our team has helped them optimize for inference as well. So this allows you to automatically generate product listings for sellers. And with TensorRT and Triton Inference Server, the catalog team was actually able to decrease their latency by 3x and do 2 times more throughput just by using our frameworks with TensorRT that optimize the inference as well. Another team that we've worked on with is Amazon Music. So this is their spell correction model. It allows you to, for when they're doing searching, automatically spell correct the input. And with TensorRT, we were able to, and Triton, we were able to get a 63% reduction in latency versus CPUs, 73% reduction versus CPUs, a 25 millisecond end-to-end latency. And then also our team helped them with tensor cores and other parts of the H100 actually do a 12x reduction in training time as well, and get a major boost in GPU utilization. The last one would be Amazon Search. So this is real-time spell check as well for product search. It takes in tons of queries every time, so it has a lot of throughput and latency requirements, and we were able to get it to a sub 50 millisecond latency and deliver 5 times the throughput using Triton and TensorRT as well. And using the Triton model analyzer, something that might have taken weeks to be able to find the correct configuration can be done in hours. So some stuff about NVIDIA on AWS. So NGC, this is one of the, I think, one of the most important parts of the talk is where you can actually get all of our NVIDIA software. So NGC is where we also produce all of our containers. So you can imagine all those PyTorch dependencies and making it all work on GPUs efficiently is difficult. We have PyTorch containers, TensorFlow containers, containers for all of our frameworks as well. And then we also publish our models there as well, so you can be able to take any of the models that our internal research teams have trained and be able to use them. And so this has all of our frameworks such as BioNemo, Nemo LLM, Riva, all of those things as well. And these are all updated regularly, and they're transparent for you to be able to check that it's gone through security checks, and then you can pull them as well. We also do all of our early access through NGC, so if you sign up for early access, say for our multimodal containers, you can get that through NGC as well. And it makes it for a lot simpler deployment and use. Okay, so just wanted to go through kind of what I was talking about when I said that we have frameworks at every single level. These are just a couple examples. So you can think of Rapid, Spark, cuOpt. These are drop-in replacements to be GPU accelerated for data science and analytics as well. Or QML you can think of as the drop-in replacement for stuff like scikit-learn. And then for recommender systems, we have Merlin. And so this is for all of those huge embedding tables and being able to manage all those DLRMs. Merlin can help you with that, and that's all GPU optimized for being able to use for super large workloads as well. For speech and vision, we have Tau and Riva and DeepStream. So DeepStream allows you to be able to optimize the video input and all of the pre-processing that goes on there. And then with Tau, you can automatically have optimized training and inference models for your computer vision workloads. And Riva is our speech one. And then for inference, which Jahan will be talking about later, we have the Triton inference server. So this is an inference server that allows you to easily deploy your models, whether it's a different TensorRT backend, a Python backend, or any other backend, and be able to manage those requests and optimize for it. And the last one that we'll be going into a little bit is NLP, and also more generally generative AI, is our Nemo framework. And this is our framework that allows you to train, fine-tune, and also deploy all of the super large models that are coming out these days. So just quickly, we have the NVIDIA H100. So this would be the P5 instance on AWS. So this was one of our newest chips that has come out and is now generally available on AWS. It has the second generation MIG, which allows you to take a single GPU and split it up to 7 fully differentiated workloads so that they don't run into each other at all. The transformer engine, which is one of our newest features for being able to train some of these really large models. It allows you to do FP8, and I'll show you a little bit of that in a second, which is a lower precision, which means you can go a lot faster and have a lot less memory usage as well. It also has 4th gen NVLink for a lot faster performance between the networking between the GPUs, DPX instructions, and then also confidential computing as well. So the H100 is great for a lot of these super large generative models for LLMs. You can see that just from the A100 to the H100, we can get a 4x reduction in training time for some of these super large models. The p-tuning times go down drastically as well by about 5x. And also the inference throughputs for being able to use an A100 versus an H100, there's a drastic difference as well. This is because we now have faster memory, faster networking, the actual GPUs are faster, and with FP8, you can just squeeze out even more performance in terms of inference as well, and for training. So a little bit more into the transformer engine. So this is what is one of the biggest optimizations that came with the H100 besides just having faster chips, is it allows for 6 times faster training and inference because it will dynamically adapt the 16-bit and 16-bit and 8-bit math within your network. So operations in your network, so a lot of the gems, can actually be done in a lower precision and accumulated in a higher one and without a loss to accuracy. And so when you're running at these lower precisions, you get a lot better performance and it's a lot faster. And it's a little bit kind of confusing, but it's a transformer engine is actually part of the chip. But we also have a library called Transformer Engine that's all open source in GitHub and allows you to have these layers that can be automatically replaced in your regular PyTorch code. So if you have a PyTorch linear layer or another or a transformer block, you can just, instead of importing from PyTorch, you can import from Transformer Engine. It'll run an A100, H100, and that same code can automatically be used with FP8 and do all the optimizations for you as well. And all these different blocks can be fully configurable if you want to take a certain layer from a transformer engine, or you want to take the whole transformer engine, the whole block, so a whole GPT model or something like that from the transformer engine as well can be taken from the GitHub. Just we want to touch on the A100, which is also generally available. This is our last Ampere GPU that is used for a lot of the large-scale training or a lot of the inference as well on some of these larger models. So this would be your P4 or your P4DE, the difference being the P4D is 40 gig per GPU, P4DE is the 80 gig GPU as well. And this is, has all the tensor cores. It doesn't have the FP8, but it can do all the BF16 FP16 training, all of the mixed precision training that you know for some of these larger models. And this is just a broad overview of the major GPUs that are on Amazon EC2. So you have your T4s. This is kind of the one that a lot of people know as the ML inference one. This is what a lot of people run their smaller networks on because it's super cheap, so it's a good cost per performance GPU as well. And that is the G4 instance. And then the G5G instance, your T4G, is mostly for your graphics workloads and your gaming workloads where it's not necessarily ML workloads, but you can run your graphics workloads on there as well. The G5 instance is the A10G, which we already mentioned. This is for some of the best performance for graphics in HPC and also cost-effective inference. It's got a little bit more memory than the T4. It's also Ampere, so it has faster performance. You can do all of your inference there, and that's the one that we see a lot of people deploying on right now is the A10G, just because it's a good price performance for your inference. There's the A100, as we already mentioned, the P4, P4DE. This is ML training HP, being able to scale up with good networking. And then the newest one is the H100, which is your P5 instance. And then obviously today we announced that we also have the H200 and the Grace H200 as well that are coming to AWS as well. That will be for scaling out to even larger and larger models with better networking and better performance and larger memory. Okay, so now I'm just going to go through the training of the generative models. This is where we're going to get into the frameworks. The main framework is the NeMo framework. So this is an end-to-end framework for generative AI that our team has been building. So it has everything from the data curation, and we'll go into that a little bit later, to the distributed training. So how do I take these huge models that won't fit into a single GPU and be able to distribute them across thousands and thousands of GPUs without losing the efficiency with all the networking overhead and all of that comes with that. Also, model customization. So obviously right now in research, there's a lot of different techniques for model customization, your P-tunings, all of those. We have algorithms within NeMo that you can take your pre-trained models or your models that you trained within NeMo and be able to do all of this SFT, all of the fine-tuning on those models that you'd want to do as well. Then with these models that you've built within NeMo, you can then take our NeMo inference containers and be able to automatically deploy them with TensorRT, LLM, and Triton. And so you don't have to go through the arduous process of manually having to try and convert some of these models into inference-friendly formats and be able to deploy them. Our team has already been able to manage a lot of these platforms, and it's continuing to get better for an ease of transition from training to inference. And then at the end, there's guardrails, which is similar to, I guess, what was announced at AWS today. So guardrails is how is our open source repository where it allows you to be able to direct your model to be able to do inference without having hallucinations or maybe information leaking into your model that you don't want it to when it goes to retrieve something as well. And so this is generally available with NVIDIA Enterprise. And then we also have a multimodal container, which we'll go into again, which is in early access. If you can apply, you can be able to get access to that. And so that's for all of your text-to-image, image-to-text models as well. That can all be trained with NeMo as well. So as I just mentioned, we support model architectures across different modalities. So you have your basic language models. These are your GPTs, your T5s, your BERTs, your encoder, decoder, your decoder models are all supported as well. Text-to-image models, so this is Stable Diffusion, Image Gen, Clip, different vision transformers as well. And then image-to-image as well with Dream Booth, Instruct to Pix. And then another one that I want to mention is we also have support for Lava. That's also with how do you combine image and text, kind of what you would see with like a ChatGPT as well. So building generative AI foundation models is a really difficult process. So you have mountains of this training data that is very difficult to curate, to be able to put into your model and make sure that it's training not on stuff that you don't want it to be able to train on, and also how do you manage all this training data as well. You also have the massive infrastructure that you have to manage. When you're scaling out, tons of problems happen. How do I organize it so that I'm getting the best performance, and also I'm not losing any of that performance because of how I'm configuring my software as well. And then the other part that's really difficult is you also have to have the people that have the technical skills to do this. One thing is a lot of people might be good at doing deep learning. When you're going to scale, everything kind of gets goes a little wide, and it's like a lot harder and a different skill than what you might have from a regular deep learning practitioner. So there's a different skill set here as well that you need, and the hope is that NeMo will help kind of ease you into this and make it a lot easier to be able to run these larger and larger models. And then how do you also manage these complex algorithms? Building an algorithm that works across all of these different nodes is really difficult. Debugging parallel programs across all of these can be hard. And so NeMo provides that out of the box through our different tools. And we'll go into those a little bit as well. So this is, at a high level, these are all the different pain points that we're hoping to solve with NeMo. So large-scale data processing. We have data curation and data pre-processing tools. We have multilingual data support through rope, and then also being able to go to longer sequence lengths through rope interpolation as well. Finding the optimal hyperparameters, doing these large sweeps to be able to find the configuration that runs the best. We have the hyperparameter tool. Convergence of models. So it's a lot harder to go find the recipe that works to do a convergence of a large language model. You don't want to be running that tons of times. So our team internally has verified recipes for what the learning rates, what do the schedules look like for all of these GPT and T5 models, so you don't actually have to go do that yourself. And then we also, obviously, it works on the cloud. So on AWS, we automatically have tools to be able to scale up to your node counts, whatever number of GPUs, whatever model you want. And then we can also deploy inference and deploy at scale automatically through TensorRT LLM and through Triton Inference Server, which Jahan will be talking about a little later. And then we also have some tools for being able to benchmark your models automatically so that you can see how they're doing, such as MMLU or any of these tools. And we'll be open sourcing actually a new tool, I believe, soon for being able to just take a NeMo model and automatically test it against all these open source benchmarks that everybody loves to compete on as well. And again, also, we have FP8 support automatically, all the recipes in there for you to train FP8 right onto Hopper as well. So if you're on A100 right now, you want to move to Hopper, you can do it automatically and get the FP8. So the first one I want to talk about is the data curation tool. So this is the tool for taking these large pre-trained data sets. They're often trained on trillions and trillions of tokens. So how do I go through the internet, pull all that down, and then go through the curation process? So we have a GPU accelerated tool called the data curation tool. And so this will download it, extract it, deduplicate, filter the documents, and do it at scale in a performant way. And so this can be HTML, LaTeX files, different PDFs can be downloaded, and then do the language detection on them to make sure, hey, I only want English or French, or I want these languages in it, filter them out. And then we have GPU accelerated document level deduplication, so fuzzy deduplication and exact deduplication. And then we also have some document level quality filtering, so you only want the highest level quality documents inside of your training data, because what you train on is what your model you're going to get out is. If you have bad data in there that's a little messed up, you're going to have a model that's messed up as well that's going to be reproducing these things as well. So we have these different filtering techniques that are in there that are GPU accelerated as well. And then also different task deduplication as well. So at the core, where all the power of NeMo comes from is called Megatron Core. So if you're familiar with Megatron, it was the original paper that we had with all these different parallels and techniques that allowed us to train that 530B model. I think it was about 3 years ago now. And we now have it in Megatron Core. And so this is a PyTorch-based library for scaling any of your transformer models. It has all of your core blocks that you need for being able to build your LLMs or different also multimodal models as well. So inside of here, we have tensor parallelism, pipeline parallelism, a distributed optimizer. This is similar to what you'd think of as FSDP or Zero. We recently released expert parallelism for a mixture of expert models. So how do you actually, if you have tons of different experts, they don't fit on one GPU, so how do you go distribute those as well? Distributed checkpointing, and all of these are modular transformer layers as well, so you can specify, I want this activation, I want this layer, and build them. And then we also, within it, have already configured GPT, BERT, T5 models as well, and different data sets as well, so you can take your data, put it into a format that's performant, be able to train it. One thing that I just wanted to go through quickly is kind of what are these different parallelisms that are in it. Won't go into the details very high level, but these are what we usually refer to as 3D parallelism. So if you're familiar with data parallelism, where you're taking the model and you completely duplicate it across different models and they get different data. 3D parallelism is what we commonly use to be able to get actually better performance out of scaling these models, because the model no longer fits on a single GPU. So you have to split up the model itself. So tensor parallelism for training is intra-level parallelism. So this is where you horizontally split your model's layers. So you can imagine in this model right here, the layers 0 through 5, each layer is actually split into different GPUs. So if you're tensor parallelism 2, each layer is split into 2 different GPUs, and it's doing communication to be able to accumulate these, the data so that you get the same as you would if you were running on a single GPU as well. It reduces the amount of computation on each worker, which is great, but it allows you to scale up to a much larger model that no longer fits. And it's actually a lot easier to be able to implement for most models because it's actually pretty simple, and it allows for good, strong scaling. Most of the time, we use tensor parallelism within a single node. So because in a single node, you have NVLink, where you get really good networking, and so it scales really well within a node. Now, the third way of the 3D parallelism is pipeline parallelism. And so this is where you're vertically splitting your layers. So GPU 0 might get layers 0 and 1. The second GPU might get 2 and 3, so on and so forth. And so this one is a little bit harder to actually implement for most generic models, but it allows for you to be able to scale even farther than just with tensor parallelism as well. And there are certain techniques that we've also implemented within the Megatron core, such as interleave scheduling, to reduce these pipeline bubbles as well. And all of these parallelisms are already implemented for all of your common GPT models that you might want to use. And the last parallelism that I'll talk about in Megatron core would be sequence parallelism. And so this is where we're actually splitting the tensors along the time and sequence dimension. And so this allows you to reduce the memory consumption from the activation tensors and be able to reduce your activation memory as well. And with this in the same paper, and these are all in the Megatron papers, we have selective activation recomputation. And so this is where you have the memory and compute trade-off. So we actually are able to selectively say, hey, these are the operations that take up a lot of memory, but they don't take that much compute. And so maybe we offload those and we recompute those in the backwards pass. And so this is a really efficient way to be able to do reductions in activation memory. And coming up, we have actually an extension of this called context parallelism that is in Megatron core right now and will be released in NeMo that will allow you to scale up to those super large sequence lengths. So for all of these models you might be seeing where they have 100,000 context length, the problem becomes where do I put the memory if I have all these activations that are blowing up because now my sequence length is long. We have a new, I guess it would be like 4D parallelism. I don't know what they call it, but it allows us to go up to, say, 100,000, 125,000 context lengths and be able to train those models as well. So the impact of high-cost training LLMs. So there's the economic impact. It costs a lot of money to be able to do this. There's the environmental impact. Running through all of this energy is costly as well. And the barrier to entry can be hard because you need all of your engineers to be able to use it. You need to be all the money. And there's also resource contention. So a lot of you people have a cluster that's shared behind a bunch of researchers. And they're all trying to use the compute for their own research. So being efficient and being able to use these LLMs becomes a difficulty because you now are taking away resources from other researchers as well. And so what is actually driving this? It's not just that it's the data set size, the model size, the training volume. There's also inefficiencies in how we approach these that we're redoing some of these things that NeMo hopes to help. So to get a stable hyperparameter configuration, it might take multiple runs. To get better scaling efficiency, you might have to configure your model parallelism, those tensor parallelism, pipeline parallelisms differently, and different inference tests and different tests along the way to be able to find the correct configuration for you to be able to train your model. And the hope is that NeMo has tools and different pre-configured configurations that you can just take off the shelf and be able to run them so you're not spending all of this money doing these tests that have already been done for you. And so one tool that I wanted to highlight in NeMo is the auto-configurator tool. It's got two different steps. You can put your training constraints in or your inference constraints in, and it'll take these and it'll give you back a model size and a configuration for you. So it might, and we'll go into this a little bit, but it would be like, hey, I've got this much compute and I've got this much data, what should my model size be? But a lot of people go in and they already have a model size that they actually want to be able to run with, so that's fine. You can be able to take your own model size and then put it into the second stage of this pipeline, which is the efficient hyperparameter search. And so it'll take your model configuration. So for example, I want to train a 30B GPT style model, and it'll automatically do an optimized training grid search on the model parameters to be able to find a configuration that will give you the fastest performance. So we've already done a lot of tests on what the good TP, PP, distributed optimizers. There's 1,000 different ways you can configure these things across thousands of GPUs. And we do an efficient grid search for it so you don't spend all of that time trying to find it manually. I've seen a lot of people take a lot of time just trying to manually find what's the correct TP size or the PP size that gets me the lowest iteration time. We have a tool that'll automatically do that for you. So an example of what an input might be, it could be the model size, it could be the number of GPUs, the vocab size, the tokens, and then it'll run the grid search on those parameters to be able to find out what's the best performance. And you can also find training constraints as well, as I mentioned. So you could say, hey, I have a GPT-3 model. I want to run for 16 nodes for 6 days. And it might say, hey, the 5B parameter model is the best way to go about this. And there's different scaling laws that it can use to be able to find that configuration for you. So we also work with a bunch of different foundation models. So NeMo, our team produces our own foundation models in different sizes. So for example, GPT-8B for if you need faster responses, you don't necessarily need the accuracy at the higher levels. Or there's different balances between accuracy and latency at a GPT-22 that we produced. Or the complex tasks for the larger models, you can use GPT-43B, which is much larger. We also support different community models, and we're continuing to add new models over and over again as they come out for what the state of the art is. So Falcon, Llama, MPT, StarCoder are already supported out of the box with NeMo for you to be able to use them as well. So we also have a suite of model customization tools. So I know a lot of people don't necessarily just do pre-training because that costs a lot of money, but you can also do different fine-tuning, and it's at different levels of complexity for what you need. So we have prompt engineering, where you can be able to configure your prompt to get the best performance out of your model. And this is at a lower level, simple. You don't necessarily need to modify or train the model itself. There's also p-tuning and prompt learning, where you're actually learning the tokens that are appended on. And so you might have a small data set, and you can tune the actual prompts or the p-tuning as well to be able to be more suited for your task so that you can take one of these foundation models and make sure it works on your task. Then we also have, the next stage would be parameter-efficient fine-tuning. And so these are like LoRa or different adapters that you actually are training a small subset of weights that are then added back to your model itself, LoRa being probably the most famous one that's used. That is also supported out of the box, being able to fine-tune on your data set to be able to use. And then at the highest level, you have instruction fine-tuning. This is one of the more complex ways to do this. So you have supervised fine-tuning and RLHF, which I'll talk about in a little bit, for the highest level of you need to fine-tune for your task as well. So as you think, thinking about this, if you have a model for model customization, if you have an enterprise LLM that you've maybe pre-trained, or you've taken one that's one of these community models, you could take the foundation model, bring it into NeMo, do prompt learning, could do supervised fine-tuning, reinforcement learning, a combination of them. These can all be used together. And then you could deploy your model for inference with something like information retrieval on your own data, so that it knows your data sets as well. So just a little quick intro to what RLHF is that we support. And RLHF it's one of the more impressive things within our NeMo framework because it's a very hard thing to do efficiently because you actually have multiple models that are all training and they have to be distributed efficiently, and it's very complex. So you have your supervised fine-tuning, which is the first stage, which you have some prompt and responses that you fine-tune your model on. So there may be a question. If you want to be a question and answer LLM, you have questions with answers. It fine-tunes on it first. And then with human feedback, where you have collected a data set of what humans think are the correct responses to different questions, you train a reward model on this data set. And then the third step is the actual RLHF. And this is where you use PPO, which is a reinforcement learning algorithm, to be able to optimize your foundation model, usually a lot of times using the SFT model you've already trained, to be able to do the tasks that you want. So this is a very complex that requires a lot of skill to be able to do this, but we provide a lot of recipes and also very optimized code to be able to do this efficiently as well within NeMo. We also do RAG, or retrieval augmented models, as well through our Inform pipeline. And so this allows you to take an LLM, take another model that is your retriever model, and it can go and grab the context that is needed for your task from a database, say of PDFs or different data that you have within your databases, append it to your model so that it's able to answer that. So it can go and retrieve different context that it needs to be able to actually answer these models itself without necessarily doing the fine-tuning. And one of the last things I wanted to highlight is our guardrails. So one of the biggest problems is when you have these super large models, these foundation models, they're very powerful, but they can kind of go and do different things that you don't want them to do. So we have these rails that are built within guardrails that you can use to be able to take your models and be able to guide them where you are. So you have topical guardrails. If you have a medical bot, you really only want it talking about medical things. If you have a financial LLM, you only want to talk about financial stuff. You can have these guardrails that are built on top of it to be able to guide it to make sure that it's not going to go off topic. You also have safety guardrails. You don't want your model, say, producing don't want it producing certain things or outputting stuff that might be hurtful, and you can also take that out as well with these rails. And then the last one would be security guardrails. If you're getting, if you have some information that's from internally that you don't want it producing, it can be able to catch that as well, so that you're not having your LLM produce stuff that you don't want leaked. So here's just a quick slide on getting started with the NEMO framework. Feel free to reach out afterwards or come up to us after the talk, and I can point you to all the different places for where you can get NEMO framework, the multimodal container, or different parts as well. And we also have some GTC sessions that you can go through that will go a lot more in depth on the NEMO framework itself than we've had the time to go through here. But feel free to come up after the talk.
Cool. OK, thank you, Peter. So for the next part, I'm going to talk about the inference side. So before I get started, I want to do a quick poll. Have any of you heard of the Triton inference server? That's pretty cool. How about TensorRT? OK. How about Fast Transformer? OK, that's pretty good. So in the next part, I'm going to cover all of those. So first, contrary to what people usually think, inference is actually also very challenging. So this is a process that's involving multiple group of people, and usually we do it in different stages. First of all, we have ML engineers who are specialists in these models and understand how to optimize the model itself. And of course, after being optimized, we have ML ops or DevOps that's going to deploy this model into actual production so that we can have an API or some sort of way of exposing these APIs to our customers, to our users, to make it an actual service. So this is the part you are actually earning money back from your investment. And so let's talk about inference server for the first part. There are 6 pillars of challenges we observe from our customers. First of all, we have different kinds of models for different use cases. For example, if you are more into computer vision, you might be more into traditional convolution neural networks. And also, we have recurrent neural networks, graph neural networks, and even traditional ML models like decision trees and others. And typically, since different people have different familiarity with frameworks, they might choose different one for these use cases. So having a unified solution is very important. Otherwise, you will have a very messed up architecture internally. And also, based on use cases, you might have different query types. For example, if you are focused on real-time use cases, you might want to send out best size 1 request so that to make sure the latency is lowest as possible. And also, if you are more into the TCO or the cost, you might want to send batched request just to reduce it. And also, with the LLM being more and more popular, streaming is also very important. Otherwise, you need to wait until the whole answer being generated to prompt out. But with streaming, you can always see generated token by token, which will give our users a much better experience. And also, in this kind of large language models requires very heavy infrastructure investments. So you might want to have hybrid infrastructure so that you can have on-prem system as well as cloud. So in order to address all these challenges, NVIDIA introduced Triton Inference Server. So Triton Inference Server is an open source software that's specially designed for fast, scalable, and simplified inference experience. So Triton supports any framework, any query type, any platform, and it's also DevOps and ML Ops ready. That means that it's always production ready, and we want our customers to have confidence of deploying them directly into production. And last but not least, since NVIDIA is a GPU specialized company, we also designed Triton to be super optimized to make sure that you can utilize your hardware to its fullest so that you can be very cost effective. So what does Triton look like? This is an architecture graph of Triton. So on the left side, you can see we have different kind of clients. You can use whatever programming language you are familiar with. We support Python, C++, and even Java. And through HTTP or gRPC protocol, you can directly send requests to the Triton Inference Server. After this payload get received, we actually have a dynamic batcher, which depending on your constraints, for example, latency, throughput, and so on, we can intelligently batch them together and then send it to a policy queue. And inside here, depending on the importance of different query types, you can assign them different priority so that your high priority task can always be executed first. And following that, we have different backends. This could be TensorFlow, PyTorch, Onyx, and of course, for best performance on GPU, we would highly recommend TensorRT, which we are going to introduce later. And along the side, we have different kind of model orchestry. So you can dynamically load and unload models based on your business need. And also, we support very detailed monitoring metrics. This include hardware utilizations, throughput, latency, and so on. So this will give you a good confidence that your service is always in good health, and it can give you quick notice if anything goes wrong. Here is just a quick summary of what kind of backend are currently supported. So we talk about TensorFlow, PyTorch, and Onyx. And also for TensorRT, that's our most optimized inference solution. And they have integration with all these frameworks as well. And in today's talk, we are also going to focus on TensorRT LLM. So this is a new package we built on top of TensorRT to provide you the best solution for these large language models. Going next, we are going to talk about what kind of general optimizations Triton is introducing to give you better utilization of your hardware. First, we have concurrent model execution. So this feature means that you can easily deploy multiple copies of the same model on one single GPU, or even multiple models if you want to host it for different kind of use cases. And also, dynamic batcher is also a very popular features we see customers enabling a lot, because as we all know, GPU are good for parallel computing. But oftentimes, when the customers are directly sending the request, they don't have this concept in mind, and so it's very easy to underutilize our GPU. So with this dynamic batching technique, we can batch all these small requests on the server side to form a larger batch in order to use the GPU to its fullest. But a very common question is, of course, this optimization is very helpful, but how do I know what kind of configuration I should set for that? For example, how many copies of model should I host on this specific GPU? And also, what kind of batch size or wait time I should configure for the dynamic batcher so I won't keep my customers waiting. That's where this model analyzer comes in. So basically, after you specify the constraint of latency, throughput, and then you can directly run this model analyzer tool to do benchmark for you. And after the benchmarking, you can see with one single line of command, we can generate a very detailed report to tell you how the model is doing under different circumstances. This will give you a better confidence of what kind of configuration you should be using, and also you can be expecting to get the similar performance in your production. Moving next, as the logic of models becoming more and more complicated, usually one model itself is not enough of handling your task. So we are introducing business logic scripting, which allows you to introduce different kind of complicated logics like conditionals, loops, and even custom control flow you want to do. On the left side, as you can see, that's a typical NLP use cases. So after you detect different language, you can actually feed it into different models. So this is a very typical of how conditional works. And on the right side, we can also run the model in a loop. So with the recent large language models, decoder only is actually one of the most popular architecture being used today. And instead of running the model just once, we actually want to run it in an auto-regressive way. So, and this features enables you to streamline the whole pipeline and make it seamless. Moving next, that's the decouple modes. So this is a feature that allows you to break the one-to-one mapping constraints of inputs and outputs. So as I explained earlier, when you have a super long context, when you ask the Gen AI model a very long questions, you don't want to wait until the whole response being generated. You may want to see the results as it's being generated so that you can easily interrupt or early stop it or even give it more detailed prompt to make sure it's generating the results you want. And for any users that's very new to Triton, we also provide a new integration called PyTriton. So this will give you a much closer experience to Flask in Python so that any customers can have a very seamless migration while benefiting all the optimizations I just talked. Cool. And currently, aside from all the success story we talked in the beginning of this, from Peter's part, we have Amazon Search, Amazon Ads, Amazon Catalog, and so many more. Here is just a short list of customers who are currently leveraging Triton to make sure they are getting best out of the GPUs. And if you are interested, here is some useful link you can check out to get you started. So these are standard GitHub link. It includes more detailed release note, and it will give you more detailed description of all these features and how they works. Next, Triton is also integrated into Amazon SageMaker. So I know a lot of you might already be super familiar with SageMaker, but if you are wondering what else you can do to boost your performance even further, Triton Inference Server's integration is definitely something you can easily check out. We provide a Triton Inference Server container directly hosted on ERC, so anyone can directly pull it and use it for your own use cases. And also, all of this can be directly involved with Amazon SageMaker Python API. We also provide very detailed code example in both NVIDIA and AWS GitHub. So with both tools combined, you can expect your application to be run in more cost-effective, flexible, and also secure. Here is some useful links you can check out. And we are also tightly collaborating with the SageMaker engineers. We also publish tons of blogs for all kinds of different use cases. So if you guys are interested, feel free to check it out. You might find your use cases already covered, so simply following the steps will give you a very seamless experience. Cool. After doing this, if the performance is still not meeting your expectation, you might be wondering, what else could you do? Is there any other technique that's focusing on the model itself you can leverage to boost the performance to another level? That is where TensorRT comes in. So it is very GPU specific, and it's internal to NVIDIA. That's why we are very confident that it should give you the optimal performance possible. So this is the same graph I'm showing before, but basically inside TensorRT, you can also optimize it for different kind of constraints, and then we make it support all kinds of GPUs NVIDIA is producing that include all the data center GPU, and also the embedded devices and so on. So a quick question is, why do you want to go this extra efforts to optimize your model? So this is just a quick summary, how much speed up you can easily get by introducing this new framework to you. As we can easily see, it's basically providing acceleration for all kinds of use cases. For computer vision, that's a 36x. For speech recognition, that's almost 600, which is astonishing. And similarly, for NLP, for transformers, for text-to-speech, and even recommenders. TensorRT is basically providing acceleration all across the board. So what is happening underneath? First of all, we are providing different kind of quantization technique. Contrary to the training process, where you may want to use higher precision so that you can make sure you have a very good performance model. During inference, we actually don't need the high accuracy. And there are also different kind of quantization technique that allows you to even go lower to int8 or FP8. And also, we provide layer and tensor fusion. So surprising to a lot of people, the performance you get on GPU can easily be bottlenecked by CPU because you are keep launching small kernels. And all those small kernels have very big CPU overhead. So by running different kind of fusion techniques, you can directly increase the utilization of GPU by forming a much larger kernel. And also we have all kinds of other techniques like dynamic tensor memory, multi-string execution, time fusion, and so on. And here's a bunch of resources you can leverage to try out TensorRT easily. But of course, you are today not only for the general TensorRT, you want something specific to large language models, to Gen AIs. And that's where we bring TensorRT LLM. So TensorRT is always a good, and it's been providing state-of-the-art performance on single GPU. But as this model grows larger and larger, single GPU is not enough of handling them. That's why we find it's very important that we need new support for this kind of large language models so you can run multi-GPU or even multi-node. So previously, NVIDIA actually have a project called Fast Transformer. It's providing very good performance, but it's also having some challenges. Because this area is developing so fast, it's always coming out with new model architecture. And since Fast Transformer is designed in C++, it's actually very hard to extend, especially for our customers. In order to resolve it, we are bringing it back into TensorRT so that we can provide a more modular API to make it easily extensible while still offering the state-of-the-art performance. And here is just a quick summary of what the current performance looks like. As you can see, it's providing SOTA performance, and it's also tightly integrated with Trident so that everything can work together to streamline your deployment. And we are also providing different kind of parallelism technique so you can split the model either using tensor parallel or pipeline parallel. Here is the architecture of what TensorRT LLM looks like underneath it. So as what we are saying, it's actually based on the TensorRT runtime, but we are bringing out all the optimized kernels we developed in Fast Transformers, and we are also introducing NICO communications, so we can run it with multi-GPU and multi-node. So currently, we already have a bunch of different pre-built models we can easily leverage. For example, if you are using GPT, Llama, all those are already supported. You can directly follow the example to run that easily. And also, in order to support all new models, we are also exposing all the underneath layers. For example, we have different kind of operations, different kind of activation layers. All those are also being exposed so that you can take it on your own to do customizations on top as well. And here is a very quick workflow, what the experience of using TensorRT looks like. So basically, after you have your model pre-trained, your original framework, this could be PyTorch, TensorFlow, or NeMo, as we just talked in the earlier in the session. You can just initialize this model in original framework and then run an engine building command. This is just one line of code using TensorRT LLM. And we are also doing tons of efforts to reduce the compilation time. For example, for today, it only takes a couple of minutes for a supergiant model. And once it's being compiled, you can directly use Python or C++ to execute it. And you also have the option to simply serve it with Trident. Another unique offering when you are using with Trident is called in-flight batching. This is a super popular technique, which is also known as ORCA. So on the top side, where is what the traditional batching looks like. So as you can see, since your inputs is likely to have different sequence lengths, you need to pad it with meaningless tokens to form a matrix so that you can fit into the model. That's where the black block represents. But with in-flight batching, instead of doing that, you can feed in arbitrary sequence lengths to have a much better utilization of the GPU. So this means that no downtime at all. So with all these features combined, here is what kind of performance you can be expecting. With GPT-J6B, you can see we can easily achieve 8x improvement. And also Llama 2, this is actually a 7B variant. So you can see it's actually not possible to fit in one single GPU. This is leveraging the tensor parallelism, and you're achieving about 5x speed up. And of course, we have more model support and more performance benchmark coming out. If you're interested, feel free to go to our GitHub and check out our blog recently published. Here is all kinds of resource you can easily leverage. We have the standard GitHub for TensorRT LLM package, and also the Triton TensorRT LLM integration. We also have a launch blog and all kinds of different API documentations you can easily refer to. Okay, with that, that concludes our inference side. So some call to actions and conclusions we can take away. So NVIDIA GPU powers most compute-intensive workload, from computer vision to speech and many more. And for training, it's always good to leverage NeMo framework. And also we have Triton, which is open source model serving solution you can use for any type of models and even any type of hardwares. And TensorRT, for absolute best performance on GPU, you might always want to check out TensorRT and TensorRT LLM if you are using large language models. And of course, if you need any help, NVIDIA is also offering AI enterprise support, which give you direct access to the experts inside NVIDIA to give you more confidence of adopting all these awesome technologies. Sounds cool. And this is actually our last slides. And feel free to stay along. If you guys have any questions, we are happy to take them.